So for this lecture, I'm going to look at in more detail what's the idea of limits in, right? So we understand why we use limit, right? Because you want to find the slope of the tangent line, or you want to find instantaneous velocity or instantaneous rate of change. But certainly it's the limit, the application of limits is widely used in many situations, including something called derivative, which we need to know later on. But let's start with the definition of the limit. But before that, I want to say that I want to go back to the first lecture and say that limits arise when we want to find the slope of the tangent line and the instantaneous velocity of an object. All right, so let me give you a definition of the limits. So suppose f of x is defined when x is near a number a, then we write limit of the functions as x approaches a is equal to L. So this is the limit. If we can make the values of f of x arbitrarily close to L, as close as we like, by restricting x to be sufficiently close to a on either side of a, but not equal to a. Right, so that's what we want, right? So there's a lot of wording here, but what you want to know is that as I make x closer to a, as close as I want, right, sufficiently close to a, I will get that the limiting value of f will be equal to L, right? So the limiting, in other words, the limiting value of f is equal to L as x approaches a. Just approaching, right? Sufficiently close to a, but not equal to a, right? And this sufficiently close to a can go either way. It can go on the right-hand side of a or the left-hand side of a. So you have this is limiting value of f is equal to L as x approaches a, but there's another way to write the notations, alternating notations. Limit of f of x equal to L as x approaches a can be written as f of x go to L as x approaches a, like that. Okay, so that's the two notations that you might want to look at. So once again, right, when you find the limit of the function or limit of something, right, you never want to consider x equal to a exactly, but you want to find something close to a. Let me draw something for you, and hopefully this makes sense to you in terms of the limits. So there I have three cases. So for the first case, let me give you some function, some random function here. So this is 0, this is a, this is L, here's the limiting value. Right, so by looking at this graph, I say that the limit of the function f of x as x approaches a is equal to L. Right. So what do I mean by that? Right. So go back to the definitions of the limits. Right. So if you let x approach to a on either side of a, right. So if you approaches a from the left, or if you approaches a from the right, what is the function approach to? Right. So where is the functions going to move? Right. So you can see that the functions. Let me use a different color here for this. So as x approaches a, right, the functions go in this way, right? Go toward the limiting value. So the question is, as x approaches a from the left, right, what do you see the curve approaches to? right? So the curve approaches to the point L. And if you look at the same graph, but now you approaches A from the right, you can see that the function is also approaches the point L. And also by looking at this graph, I can say that the function is defined at x equal to A. So how could I know that the function is defined at x equal to A? Because from recalculus, when you find the domain of the functions, right, you come to conclusion that if the domain is all real number, then the function is defined at the point on that interval. So the function is defined at x equal to A because there's no holes, right? There's no infinity at that point, right? Of the functions as x approaches A is equal to L, and the function is also defined at x equal to. So I'm going to give you another graph. So y, x, this is some function, and at this point, you have an open circle. Right, so at this point A, right, this is L, and the closed circle right here. Right, so this is similar graphs, but different situations. So the difference here is that at x equal to 8, right, the function is still defined, but at a different location compared to the previous graph. Right, so I want to say that the function is defined at x equal to A, right? So it defined right here, right? It's the closed circle right here. Right. When you have an open circle, that means the function is discontinuous at that point. But on the concept of continuity, that's another day, right? But just so you know, at this point, right, at this moment in time, when you have an open circle, that means the function is discontinuous at that point. But at that point, it's still defined because it's defined at this closed circle. And so I say that the function is defined at x equal to A, but f of A is different from L. Right? Compared to the previous graph, you see that f of A is exactly equal to L. Right? You still have the limit, which is the limit of the function as x approaches A equal to L. Right, even though f of A is different from L, the limit still exists. Right? So I use two different color here. As x approaches A from the left, the function approaches the value L. Right, so the word is approaching. It's not exactly the same. It's approaching. Right, you can get the value as close to L as possible. Right, as x go to A from the right, the function approaches that value L. Still approaching. It's not going to be exactly at that point L. I'm going to move on to the third graph. Like I say, very similar, but for the third graph, you don't have the function to be defined at A. You have an open circle right here, and there would be no closed circle. Because there's no closed circle at that x equal to A, you say that function is undefined as x equal to A. But still, you still have the limits. Right? So the limit of the function at x approaches A is equal to L. Right, so we discussed about like x approaches A from the left, x approaches A from the right. So that's the concept called the one-sided limit. Right? So one-sided limit. Right, so one-sided limit, limit of the function as x approaches A from the left, or the limit of the function as x approaches A from the right. So you have limit f of x. Right, so that is the notations that you need to be careful, right? So x approaches A from the left, there's the negative on the top right of A. So that's indicate that I want to let x approach A from the left. So left hand limit, right? So x approaches A indicate that you want to consider values that are less than a, or you want to consider values that are on the left of a. And for similar definitions, but now you have x approaches a plus, right? So indicate that you want to let x approach a from the right, right? And we call this the right hand limit. And so x approach a plus, you want to consider values that are greater than a on the right of a. Let's move on to the theorem. So existence of limits of a function. For this theorem, we say that the limits of a function exists if and only if the left-hand limit and the right-hand limit are equal to the same value. Or if you want, you can write like this, right? The limit of the function is equal to L as x approaches a if and only if the left-hand limit equal to L, and that is also equal to the right-hand limit. All right, so just to recap this theorem, because anytime you want to find a limit, you have to be able to show that the left-hand limit equal to the right-hand limit equal to the same value. When that is the case, you say that the limit exists and the value of the limit is equal to L. Otherwise, the limit does not exist. Example, so determine if the limits of the function capital H of t equal to 1 if t is greater than or equal to 0, and 0 if t is less than 0. So this is called the step function. Right, so you want to determine if the limit of the function exists as x approaches 0. Right, so you want to find the limit of capital H of t as x approaches 0 exists or not. Right, so let's draw this function. This should be a very nice enough function to draw a graph. Right. So there are two parts to this function, right? The first part, like x of t, right? So the output is equal to 1 when t is non-negative number, right? T is greater than or equal to 0. So let me draw the coordinates. So this is capital H of t. This is t. You can see that as t, H of t is equal to 1 when t is greater than or equal to 0. Right, so close circle right here. This is 1. Right, t is greater than or equal to 0. The function is equal to 1. And the second part is t when t is less than 0, the function is 0. And because there's no equal sign right here, you have to draw an open circle at the origin. So this is 0. Right, so this is the step function, and let's consider the one-side limit for this function. So limit of h of t as t approaches 0 from the right, t approach to 0 from the right, the function is going to approach to 1. So that's why I'm saying that limit of h of t as t go to 0 from the right is equal to 1. Now, what about limit of h of t as t go to 0 from the left? What do we have? Right, so t approaches 0 from the left. Right, the function is also approaches 0. So when you have 0 plus here, that means you approach 0 from the right. And when you have 0 minus here, or any value minus, that means you approach that value from the left. All right, so you can see that left-hand limit does not equal to the right-hand limit, so the limit does not exist. Makes sense to you, right? So since limit h of t as t going to 0 from the right, different from the limit of the function as t going to 0 from the left, then the limit of the function as t equal to 0 does not exist. Or you can write d and e. All right, so let's consider another example. So I would like to show that the limit of the absolute value of x as x approaches 0 is equal to 0. All right, so what's going on here? So when you look at absolute value, you know from pre-calculus for absolute value, there are two parts, the positive part and the negative part. It depends on how you choose x, right? So for the absolute value functions, there are two parts to different functions. You have positive x, right? Absolute value of x is equal to x if x is greater than or equal to 0, and is equal to negative x if x is less than 0. And therefore, when you draw this function, so one part of the curve is like that, right? So that is the function is equal to x when x is greater than or equal to 0, and another part of the function is so that is equal to, the function is equal to negative x when x is less than 0. Looking at this graph, you can say that, so what happened to limit of absolute value as x approaches 0 from the left? What's going to happen, right? So as x approaches 0 from the left, like that, this approaches 0, right? Like that, right? The function approaches 0 as well. And so I conclude that as I approach limit of the function as x approaches 0 from the left is equal to 0. What about the limit of absolute value of x as x approaches 0 from the right? You can see that, right, so you approach 0 from the right, the function also approaches 0. So the left-hand limit equal to the right-hand limit, they equal to the same value, which is 0. So therefore, by the theorem that you have earlier, the limit exists, and the value of the limit is 0. Since the left-hand limit and the right-hand limit equal to one another, then the limit exists, and the limit of the absolute value of x as x approaches 0 is equal to 0. The next example, I'm going to give you some graphs. Consider the following graph. So this is y, this is x. We're going to find a limit of the functions by looking at the graph. All right. So I have something like this. We have this type of a graph, right? So this is 1, 2, 3, 4, 5, something like that. And this is 1, 2, 3, So this is supposed to be like this, and that is the graph. The purpose of this exercise is, or this example is to find the limit of the functions using this graph. Right, so what is the limit of the function? I call this function g of x. Right, so what is the limit of g of x as x approaches 2 from the left? That's part A. Part B is the limit of the functions as x approaches 2 from the right. Right, and from that, from these two previous two questions, what is the limit of the function as x approaches 2? Okay, so as x approaches 2 from the left, where is the function approaches 2? Right, so the value is 3, right? So the function approaches 3 right there. Now, when x approaches 2 from the right, what is the value of the limits? So the left-hand limit does not equal to the right-hand limit, and therefore the limit does not exist in part C. Right? So does not exist. Right? So the explanation is that the left-hand limit does not equal to the right-hand limit. Right. Similarly, I have question like limit of the function as x approaches 5 from the left. Limit of the functions as x approaches 5 from the right, and what is the limit of the functions as x approaches 5. Right, so by looking at the graph, so limit of the function as x approaches 5 from the left, so the function approaches right here, right? So it approaches 2. X approaches 5 from the left, the function approaches 2. So as x approaches 5 from the right, where's the function heading to? So also 2 here. And therefore, you see that because the left-hand limit equal to the right-hand limit and equal to the same value, so therefore the limit of the functions as x approaches 5 equal to 2. Looking at this graph, what you can do is you can find the limit of the functions when x approaches to a certain value. Right? So in this case, approaches 2 or approaches 5. There are some cases that the function approaches infinity. Right? You learned this kind of concept when you learned about horizontal asymptote. Okay. In addition to that, you can find the limit. You can have the limits, let's say limit of the function as x approaches 2 from the left can be positive infinity or can be negative infinity. Right? So the limit has infinite value. Right? And you learn that kind of concept in pre-calculus as well under something called the vertical asymptotes. Right? So I'm going to give you some example on limits at infinity or infinite limits or something like that. Let's consider this example. Right. Consider the graph of the function f of x equal to 1 over x squared. So find the limits. Limit of 1 over x squared as x approaches 0. Right, so you want to find this limit. And the graph of the functions 1 over x squared something like that. So that's the graph of the function 1 over x squared. As you can see, the y-axis, which is x equal to 0, is the vertical asymptote. What about the limit of the functions? As x approaches 0 from the left, what is the limit of it? As x approaches 0 from the right, what is the limit of the function? Right. So as x approaches 0 from the left, right, the function's going up like this, right? Right, so therefore the functions will approach positive infinity. Now, when x approaches 0 from the right, like that, right? From the right, where's the functions going to? The functions is also going to positive infinity. No. And we are sure about this because, once again, by looking at the graph, x equal to 0 is the vertical asymptote, right? And therefore, the limit of the functions as x approaches 0 equal to positive infinity. Depends on the textbooks. Some textbooks say that the limit of this function is positive infinity, or the limit of this function does not exist. Because infinity is the concept, not an actual number. You cannot pinpoint what infinity is. So sometimes you can say that it does not exist. Right? Even though you have like positive infinity, you don't know exactly what positive infinity is. You can say it does not exist. So for vertical asymptotes, so I see that the line x equal to a is called vertical asymptote of the curve y equal to f of x if at least one of the following statements is true. All right, so I give you the statement and I also give you the graph that's corresponding to that statement. So the first one is limits of the function as x approaches a equal to positive infinity. So number 2 is limits as x approaches a from the left equal to positive. Positive or negative infinity depends on the problem. Number 3, limit of functions as x approaches a from the right can either positive infinity or negative infinity. This is not a fractions, okay? This is not a fraction. I'm just saying. Let me be careful here. So either positive infinity or negative infinity, positive infinity or negative infinity. When one of these is the case, then you have x equal to a is the vertical asymptote. Right, for number 1, you see the graph earlier, right? You see the graph earlier, and you see that the limit of the function as x approaches a is equal to positive infinity. So quick drawing for that should be something like that, right? You can have, let's say, limit of the function as x approaches a from the left is equal to positive infinity or negative infinity. So let me draw an example for that. So this is the vertical asymptote right here, right? Something like that. Or the last case, you have some vertical asymptotes, something like that, right? So the function approaches negative infinity, as x approaches a from the right. So instead of looking at the graph, we want to find the limit using algebraic method, right? So example, find the following limits. So I want to find the limit of the function 2x over x minus 3 as x approaches 3 from the right, and the limit of the functions 2x minus 3 as x approaches 3 from the left. Okay. So what is the value? What is the value of the limit? Right. So remember, we consider the limit as x approaches 3 from the right. X approaches 3 from the right is anything on the right of 3. Anything that is greater than 3. So like 3.01, 3.001, 3.0001, something like that. The closer to 3, the better, right? And when that's the case, right, so the closer to 3, the better. You can see that, right, so 2 times some positive number, right, because on the right of 3 is still a positive number. Right, on the right of 3, remember, on the right of 3, positive, right? So x minus 3 has to be a positive number as well. And therefore, you conclude that this should be a positive infinity. You follow the idea? Because I want to choose something on the right of 3, but it's very close to 3. Like I say, 3.01, 3.001, or 3.0001. Right? It's very close to 3. So that's why I got positive infinity. If you're not sure, right, if you're not sure about this, you can briefly work out the details. Let me move this out of the way for now. Like I say, you want to choose the value on the right of 3. Let's say x equal to 3.01, or x equal to 3.001, x equal to 3.00. Like if you, right, the closer to 3, the better. Right? And you substitute this value into the denominator, and you will find out that, let's say I pick this one, right? So 3.0001 minus 3 give me 0.000001, which is a very small number. When you have a very small number in the denominator, right, it will make the fraction become a very big number, big positive number in this case. So therefore, you have a positive infinity. All right, so let's move on to this part. Right. So as x approaches 3 from the left, right? So x approaches 3 from the left, you still can choose like 2.9, 2.99, or 2.99999, right? So all of these numbers on the left of 3. And if you choose this number and substitute that into the fractions, you will find out that 2.999, how many 9 is this? 1, 2, 3, 4, 5, 6, 1, 2, minus 3, you will have 0.000, or something like that. A very small number. Once again, this small number is in the denominator. I'm sorry, this is negative. This negative small number is in the denominator. So therefore, you will have something, a very big negative number. Right? So I say that 2, which is positive. The denominator is negative, so you have negative infinity. This is a good spot to stop because we're done with this lecture.